Okay, so in the previous video we talked about the fact that instruction scheduling is used to control the order instructions execute, and that the compiler can do this with the help of a data dependence graph. So we're going to describe the properties of a data dependence graph in this video, and we're going to look at one way you could use to calculate a data dependence graph. Okay, so we've talked about dependencies, data dependencies, in the previous videos, and we described them in relation to hazards. We talked about true dependencies in the form of read after write hazards. We talked about anti-dependencies because these are sometimes called write after read hazards. And we also talked about output dependencies because these are often caused by write after write hazards. Okay, but when the compiler is looking for these data dependencies, it's looking for all the possible dependencies. And so we typically don't refer to them as hazards because we need to know about them even if they're not a hazard in the pipeline. Right, so a true dependence is when one instruction writes to a register and a later instruction reads that register. And that would be like producing R1 in the add and then reading it in the subtract. And an anti-dependence occurs in the opposite scenario. Subtract is producing a register, but the previous add is reading it. This is an anti-dependence because the add needs to read R1 before subtract can write to it. And then the output dependence occurs when two instructions are writing to the same register back to back. And so it had better be the case that the later instruction is the one that actually updates the register instead of the earlier one. Right, later instructions after subtract should only see the value written by subtract and not the value written by add. Okay, so we want the compiler to find all these data dependencies and then schedule the code in a way to prevent as many data hazards as possible. Now, when we draw a data dependence graph, the way we're going to draw it is with nodes and edges, right? And we'll have a node for every instruction. And then we'll have an edge or an arc between instructions to convey different types of dependence. And we'll have a plain arrow to indicate true dependence. We'll have an arrow with a line through it to indicate anti-dependence. And then we'll have an arrow with an O on top to indicate output dependence. Okay, and then we could take a sequence of instructions, right? And so here we have instructions A through I. And so I've drawn out nodes here as just the letters for A through I. And again, I drew them in this pattern because it's useful for drawing the graph. It's not necessarily something you could figure out in advance. Yeah, I only know that I should draw it this way because I drew the graph already. And so I have a node for each instruction. And then we'll add all the edges to this graph to represent the different kinds of data dependencies. And basically what you have to do is consider every pair of instructions and the registers they use to come up with these edges. Of course, I say every pair of instructions. It's not really every pair, but what you would do is just start at A and then look through the code to see where R2 gets used. And so we don't really see a dependence until we get to instruction D, and we see that D is using R2 and that A produced R2, and so that means there would be a true dependence from A to D. And so I draw that edge into the graph. Let's see, I think that's all we can do for D. Okay, E uses R3, and R3 comes from B, so there's going to be a true dependence from B to E. And you'll also note that D reads R2 and E writes it, so that's a anti-dependence. And so we'll need to add those edges, and there's also an output dependence between A and E. Okay, so we added the true dependence from B to E, the anti-dependence from D to E, and the output dependence from A to E. Okay, moving on, we can look at F. F uses the result from D, and so there'll be a true dependence there, and it uses the result from B, and so there'll be a true dependence there. And so we can add those two edges in. Okay, and then we look at G. G needs the value from R5, and then it produces a new value for R5. So that means it has both a true and an output dependence with respect to F. H uses R5, so it'll have a true dependence with respect to G. And then I, instruction I, uses R4 from instruction C, and it uses R2 from instruction E. Okay, and so that would be our complete data dependence graph. Okay, and then we could use this set of relationships to know how to schedule the code. Right, there's a lot of information in these edges. For example, since there's no edge connecting A and B or A and C, then A, B, and C could all execute at the same time. But since there is an edge connecting E and I, then E and I have to execute in sequence. Okay, so this data dependence graph tells us a lot about the available possible orderings of the program. Okay, now how do we actually compute this? Well, we would get a list of instructions. We would want an algorithm that takes in a list of instructions and produces as output this data dependence graph, or this data dependence information in some way. And so what we're going to assume for our implementation is that each instruction has a unique identifier between 1 and n, because this makes it easy to index. Though in my slides I'm going to show them labeled from A to I, like in my previous slide, but you can imagine A to I is the same as, 1 to some number. Then for each type of, for each register, we're going to track which instruction last defined it and which instructions have used it. And for each type of dependence, we're going to have an n by n matrix of integers. That means that if there's a 1 in the matrix at a position, then there's an edge from between two instructions. And if there's a 0, then there's not an edge. Okay, and a matrix is often used to represent edges in a graph. Okay, so here's what our data structures would look like. I'll have this struct instruction for all the different LC3 instructions that I'm showing you. So I'm going to have this one struct that represents all the source registers. I'm sorry, I have this one field representing all the source registers. I have another field representing the destination register. And then I have the number that represents the unique ID number for the instruction. Then I will have I'll have an array. And this array will be long enough to represent every register in the instruction set. And inside this array, I'll remember the last instruction that defined this register. And I'll also have another array which remembers remembers the set of instructions that have used a register. Okay, and then I have three matrices, flow arc, anti-arc, and output arc. And this represents true dependences, right, and anti-dependences and output dependences. And if I have a dependence from instruction 1 to instruction 3, then I'll set that entry in the matrix at 1, 3 to 1. Right, so I'll initialize these matrices to 0, and I'll only set entries in the matrix to 1 if there is actually a dependence between those two instructions. All right, and then this is what the algorithm would look like. I just need to visit each instruction in the instruction list once. And then when I do that, I'm going to do some bookkeeping so I can figure out all the dependencies. The first kind of dependence I'm going to look for is a true dependence. And what I'm going to say is that, excuse me, is for every source register in the current instruction, then look to see if there was a previous instruction that defined that register. And if there was a previous instruction that defined that register, then we'll set the entry in the flow arc to record that there is a true dependency using the ID number for the defining instruction and the ID number for the current instruction. And this will detect a true dependence. Okay, next we'll look to see if the current instruction has a destination register, and if there was a previous instruction that defined the same register, then we'll set an output dependence from the defining instruction to our current instruction. Okay. Now, if this instruction we're currently analyzing defines a register, then that means there would be an antidependence from those previous instructions to our current instruction. And so we're going to look in the usinst list at all of the instructions that have used the current destination register. And for all of those, we set an edge from that previous instruction X to the current instruction. Okay, and that will track all our antidependencies. For every instruction used by the current one, by I, for every register used, we add it to the usinst list so that we can track future antidependencies. And then if the current destination register is not null, then we clear the used instruction list for this register, and we set the defining instruction for this register, for this current register i.dest to be this instruction. Okay, and then that way, future instructions that use the register create a dependence to this instruction that we're currently analyzing. Okay, and we just do these steps for every instruction in the list, and this will build our data dependence graph for us. So I'm going to walk you through this. You may want to stop and print out this slide of code so you can reference it while you walk through the steps. Okay, so in step 1, we'll deal with instruction A. And instruction A is going to define register 2. And so in the spot for register 2, we indicate that that's instruction A. Okay, I also recommend that you print out the instructions, right, so that you can go back to slide 29 and print out the code there so you can follow along. So we're going to deal with, so by step 1 I mean we're dealing with instruction A. And instruction A defines register 2. And so in this definst array, we'll mark the register 2, so this is 0, 1, 2 in the array, right? So the index 2 is where we'll track the fact that instruction A defines that register. Okay, and there's nothing else to do because this is the first instruction and all the other entries in the arrays are empty, we just move on to the next instruction. And then instruction B, in step 2, will set that the defining instruction for register 3 is instruction B. Okay, and there's nothing else for us to do now either. And then the same thing happens for step 3. We set that the defining instruction for register 4 is instruction C. Okay, now we go into instruction D. And now something more interesting happens. D, we're going to look at its source registers, and D uses register 2. And so we'll look to see what instruction used register 2. And that would be instruction A. And so that means we're going to update this matrix to say there's a true dependence from A to D. We would also look to see are there any instructions, previous instructions, that use register 1? But there aren't any, so there's no antidependence. And there's also no previous instruction that defined register 1, right? Register 1 was empty before, so there's no output dependence. And so we're done just marking that. The other thing we do is we mark D as the instruction that defines register 1, and we mark D also as a user of register 2. Now we go to step 5 where we deal with instruction E. And now when we're dealing with instruction E, we'll look to see, instruction E uses R3, and so we will look up R3 and see that it comes from B, and so we'll create a true dependence from B to E. Okay. We also see that E defines R2, and so we will add an output dependence from A to E, because A is the last instruction that defined R2. And we also see that E defines R2, and that D was the previous use. I'm sorry. I should see D here in this list. If we go back one step, we see that D was the previous user of R2. So we'll also have an anti-dependence from D to E that shows up here in this middle matrix. Again, then after we do that, we update E to be the instruction that defined R2, and we clear, that defines R2, and we also clear the use list for R2 to say that it's empty. And then we make E a user of R3. Okay, now we go to instruction F, and we do the exact same thing. And when we walk through these data structures to figure out what dependencies that there are on F, we'll figure out that there is a flow dependence from B to F, and a flow dependence from D to F, and that's all. So then we handle G, and we'll update these matrices for G, and H and I shown here in step 8 and step 9. And one thing you'll see here is that when we're dealing with, as we add more instructions here, then actually the use list for these registers can fill up, and you can have multiple registers in the use list. And that means that if we ever redefine that register, in this case, if we were ever to redefine R3, we'd actually have a lot of anti-dependencies, because we'd have anti-dependencies coming from E and F to whatever instruction defined R3. And that's the reason we're tracking these here. You also see that eventually we fill up a lot of this defense register with different instructions because they're all defined in different registers. Okay, but ultimately after we go through this whole algorithm, we look at each instruction, then we fill up these matrices, and then you could use this matrix to draw the exact same graph I showed you earlier by looking at every black square in this flow arc matrix. And so you would draw an edge from A to D, an edge from B to E and B to F, an edge from D to F, an edge from C to I, an edge from E to I, an edge from F to G, and an edge from G to H. You would draw an anti-dependence from D to E. Then you would draw two output dependencies from A to E and from F to G. And those, in fact, are the ones we drew earlier when we walked through the graph. Of course, that's not excellent, because I knew that would be the right answer. Okay, so the most important thing is that if you had a piece of code that you could draw out this graph, you don't really need to know the algorithm per se, but the algorithm may help you at first to identify which edges really matter. But after you do it a few times, you know, the most important thing is that you're able to draw this graph, this data dependence graph, from a set of instructions. Thanks.